Hello guys, I hope that you will be really very fine this day. Today in this video I'm just going to make you learn how to simple add the two numbers using the code in Quartus software, and after that we will learn how to make the arithmetic logic units, and also we will make the circuit, or you can say that code that is consisted of the statements that usually works on the principle of the mux, that is if the selection line bit are 0000, then it will perform addition, but if it is 1, then you can see that here it is performing um, the complement, subtraction, greater than, lesser than, and shift operators right, and shift operator left, and a into b, and a divided by b is greater than 1 or b is lesser than 1. So here you can see that these are the different types of the operators that are used, but basically it is the logic, you can say that it is the logic of the mux that is being used here, because there are the selection lines in the mux. Depending upon what the bit that you're providing to it, it will perform the operation and give you the output in the form of that. So I will let you now the first exercise. This is the first exercise of this entire lab that I'm performing this video today. This is module and DLT lab 09 that I have already named here and here. So this is a name that should match with your renaming lab. So there are the total number of inputs and the outputs. Here you will see that, and the output is sum. So I am providing the 7-bit input and 7-bit input at B, and the output is also 7-bit. And here you can see that it is adding, and now I'm just going to see the university VWF file to see the graph. Here you will go to the edit, and then um, go to the node finder, and then list, and then just shift this only input groups at this side. Here you will see that the output group and sum, the total number of 2 inputs and 1 output, that is the sum, and then you click OK, and then click OK. So there are the two these values inputs will be appeared here. So I'm double clicking. uh, you can also change the value from here, and you can see that for example, if I'm going to apply 0 1 0 0 1 0 1, it is actually 8-bit value. So let me show it that it is 8-bit, so it is 8-bit value. Here I have inserted, and also I will just click on the question mark, and again add these values with some arbitrary number, for example 1 0 1 1 0 1 0. So you'll also see that it is 7-bit, so I am just again putting 1 here, and then you will perform addition. So I'm just going to simulate the functional simulation, and then click yes. Here you will see that I'm just save the waveform, and again you will see that the uh, this will be appeared, and after a short period of time it will be successfully compiled. Let's see what's happened next, and here we go. So here you can see that the sum at the output is 0 0 0 0 0 0. So let's make it clear that 1 1 is equals to 0, and the carry output will be 1 at here, and the addition of 1 and 1 is 0 again, and then it is added to this one, and then this is 0. So this will also add to this one, and this will also become 0, and then the carry output will go towards here. And here you can see that the output exact 0 0 is obtained as we were expecting. So I'm just going to change the value in order to show you that how this it works properly. So let's change the value like this. I'm just going to put here um, let's suppose 0000. So here you can see that I've just put the value here 0000, and then clicking OK. Again I will compile um, this as well. Sorry, I just clicked the wrong um, just compile here and then clicking the yes, and then here you will see that it will take a bit time to be compiled in order to show you that it's adding properly or not. So here you can see that 1101 and the sum like this is appeared here, and you can see that this is working properly. So let's come towards the next exercise, that is exercise number 2. Sorry, let me show you first the RTL view for the exercise number 1. So I'll just going towards this and then just click locate node and locate in RTL viewer. So here you will see that the RTL view will be appeared here. As you can see that it is adding the two 7-bit numbers, and after just performing the addition and the sum, the output will be given like that. So now come towards the exercise number 2. So here is exercise number 2. Here you can see that um, let me make some things clear, that this is the module for this circuit, and here you will see that this is simply uh, the addition that I performed above, and here you can see that the module DLD Lab 9 is same as the above that I've shown here already in exercise number 1, and this is the 7-bit value, oh sorry, 8-bit value, and here is also the 8-bit input values, and there is also the third value that is carry in. So the output will also be the 8-bit value, but if we provide the carry in, means that if I am giving the carry in, then it will give the output sum, but with the addition of the carry in as the output. So let's do the simple experiment on this in RTL view. Here you can see that this RTL view is just based upon these 8 adders, that each adder is 1 bit. So if I just zoom, so you can see that these are connected in such a way that each value of 8-bit is appearing at every single adder, and you can see that these are connected in parallel with each other. These are more complex circuit that just divide the values on each adder, but it is simply showing that the 0th and 1st and first and second bit will go towards this adder. It is simply performing the addition by data C and data D, and taking the carry in into the data B, and then performing the C out, means that this is the carry out, and this is the sum out that will maybe go towards the second adder, and here you can see that these two inputs will go towards the second adder from the output C out and share out. So this was the RTL view that is simple but not too much complex. So now I'm going towards the simulation waveform. Actually, I've already compiled this, but I'm now this time I'm just going to change the 8-bit values. Let's see. I'm just going to apply 10110111. So here you can see that this is the 8-bit value, and after that you can see that I'm just going to apply this value with some arbitrary value. So here you can see that after the successful compilation and inserting the values, here in the only in the input. Okay, and then after the compilation here you will see that the values and the output like this will be here. Actually I've applied also apply the values at the output, but you can see here that the values of the output are also changed 001 00110. So now these values are changed. So here you can see that when after performing addition you will see that these 1 and 0 are adding, then this is giving us the output with the sum of x, y and carry in. It will simply add carry in and then give us the output. So here is the example number 3. Here you can see that the lab is just named as I have renamed the lab, and after that you can see here the two inputs and the two outputs, just like x and y are the 7-bit values, but the 8 7-bit value is the sum, and here is the output, that is CO, means that it is carry output. You can name it by your own self, whatever, COUT or whatever. So this is the wire that is the internal wire. If we don't declare this wire, then there will be an error in the code, because the output and the inputs, when we declare that, these work as input output wire. But if there is an internal wire that is connecting the two logic gates that are used in the adder circuits, so it will really cause troubles. So this is necessary element that is used to declare in this code. And after that I've just assigned a temp value that is equals to x plus y, means that temp is equals to x, y, and then this is a temporary wire, and that will go towards the sum, that is as it will be equal to the 7 bits of the temp, and the 8th bit will be go towards the output, C out, that is generally known as the carry output. So here you can see that if we add, for example, um, a 4-bit number, then if the number exceeds the sum exceeds the 4-bit value, then it may be 5. But so this is the necessary condition to put the wire in 8-bit value, so as to divide it into the uh, 8-bit, and the 9th bit is this. Actually this is 9-bit, sorry for that. These are 8-bit values and this is the 9-bit. So the 9th bit will be the carry output. So next go towards the RTL view. Here you can see that the RTL view is x, y, that is the 8-bit value, and after the addition the 1 bit will be go towards the carry output, and the 8-bit will be appeared at the addition. And here you can see that the output and the sum is not appearing after just randomly applying the values. This is the output, you can see. For example, this is 1 and 0. If I add 1 and 0, then the output will be 1, and then 1 1 is equals to 0, and carry 1 and 1 0 is equals to 1. So this is showing that at the end of the score it is 1 1. So the carry output will be 1, that is exceeding the 8-bit value. This will go towards the carry out. So here is the exercise number 4, and this is the same name as above. The total number of the inputs, and let me make sure that this is the x input and this is y input. Cn is the carry input, and sum is the addition of these x, y, and Cn means the carry input, and C out is the carry output. Same process like the above example is uh, here, but the small change is here that we are applying the carry input here. So here you can see that C or is the carry output, and the wire will be consisted of these 8 bit values, 9 bit values, and just 8 bit values will go towards sum, that is the sum of x, y, and c, and the ninth bit, the last bit, that will go towards the value that is the carry output, and there comes the end module. So here I'm just going to simply give the value of C, and means the carry input 1, and then arbitrary values to these both inputs. And then here you will see that after the successful compilation, I've already compiled to reduce the time for video. Here you can see that I have just applied B, the only one bit, that is the carry input 1, and then B and X and Y, the arbitrary values. And here you can see that the C out will be 0, and sum will be 1 1 0 1 1 0 1 1 1 0 0. So after, you can see that after summing this circuit, means that 0 1 is equals to 1 will be added here, and after that 1 1 equals to 0, and there come ones, the carry uh, out 1 will be added to this, and then it will again be 0, and then 1 0 0, means that the carry output 1 will be appeared at the third carry, as a third carry, and then it will add it to 0, means that 0 1 is equals to 1, and then again 1 0 is equals to 1, and 1 0 is equals to 1, and then there comes 1 1, that is equals to 0, and then here you can see that the carry output is 0, because there is no any value left, all the values are added just like this. And here is the RTL view for this circuit, and this is the circuit as in the previous example, but only the change here is that there is an extra box that is like there for the carry output. Is just taking the C in, and summation out will be appeared here, and this is the simple circuit and the RTL view. So don't be confused it with the previous circuit, and we will see that in the next example, example number 5, where we will use the module and assign always a statement. Just we will perform the operation addition subtraction by applying 1 and 0, means that it will simply work as a full adder circuit with some control knobs, means that if we apply this is the circuit that is generally used in DLD with the an amount of the exclusive OR gates, means that the combination is in such a way when we apply the one at the one terminal, that is the control knob of that gate, that is a summer circuit. So if we apply 1, the subtraction is performed, and if we apply 1 bit value of 0, then the addition is performed. So this example is generally comprises of this. So let's uncomment it. So here is the exercise number 5, in which this is already discussed. Then we were applying bit 1 and the 0 value. So if 0, then addition will be performed, and if 1, then the subtraction will be performed. So here I've already compiled this. Before this, we have to just see this RTL view for this entire circuit. Here you can see that the additions is performed in two ways. Actually, subtraction is another form of addition, because computer generally adds, but it takes the two complement or one complement, and then after that it adds that number with the uh, above given addend. So here is the addition, and these are the circuit for the um, adder and the subtractor bit, depending upon what type of the control knob you are applying. Then here is the carry input optional value, whether you want to perform the addition or subtraction. Here I have applied 1 because I just want to perform the subtraction, and these are the two numbers that are to be added. So this is the output of these two additions, and then the temp value is the 9-bit value, that is the generally addition. And then after that you can see that the 1 bit means that the ninth bit of that temp value will be the output carry out. So after the compilation, you can see that um, I have performed the subtraction by taking the carry in 1 and just arbitrary value this like this. And here you can see that I have just applied 1 1 0 1 1 1 0 and 0 tetra 1 double 1. So here is the addition, subtraction is performing after just taking uh, the option of 1. So this is generally the a minus b, the c in, that is the bit value of 1. It will not perform any operation. It will only perform it operation in addition, because in addition the sum is a plus b plus c in. So in subtraction the c in doesn't play any role. So I hope that you will understand what I am going to make you learn. So if you really like this video, please give me the big thumbs up. If there is any query about that, don't forget to comment me in the comment section. Thank you.